So let's do an example. So let's say you have a design example. We want to have an amplifier with a gain in excess of, let's say, the voltage gain in excess of 50. And we want to have, we have a source resistance, so it's R1 of 1 kilo ohm. And let's say we have a load capacitance, so driving a capacitive load. C out of 150 femtofarads. And we are trying to use, let's say, bipolar transistors. So we have a beta, the transistor parameters of beta of 100. Let's say you have a tau f of 2 picosecond. And let's say you have a CJE and a CJC of 20 femtofarads and a CJS of 50 femtofarads. So we want to design an amplifier with these parameters. And we want to maximize the bandwidth, let's say, for now. We want to see how much we can maximize the bandwidth. Let's say, typically I give you a constraint, but I could basically just pick the value of the bandwidth that we're looking at and make that a constraint. But rather, I'm just saying that let's try to start with something and see how we can maximize that performance. So what is the basic stage you can use for an amplifier, right? What is that? What is kind of like the simplest stage that we can use? We can use a common emitter. So I have to put some sort of R2 here, VCC, V out, R1, and then there's a capacitor here. Let's call this CL. There's a source voltage here, V in. I have a capacitor C pi here, which consists of two parts, right? C pi consists of what? C pi is CJE plus CB, which is CJE plus GM tau F. We've done this before. So at GM, let's assume a GM of 40 milliamps. 1 milliamp current. So at that point, this is 20. This is 20 femtofarads. This is 2 times 20 times. I'm sorry, 2 picoseconds times 40 millisiemens. That's 80 femtofarads. So that's 100 femtofarads. C pi is 100 femtofarads. C mu, which is this capacitance, is simply CJC. So it's going to be 20 femtofarads. And CL consists of 2 elements. The explicit capacitance that you have on the output, C out, that you drive, and also the CJS, the capacitance from this collector to ground, the parasitic capacitance hanging off of the collector. So it's CJS plus C out, which basically is 50 femtofarads plus 150 femtofarads. That's 200 femtofarads. Okay. So these are the 3 capacitors that we have in this. So, tell me up front. They have to be able to tell us before doing anything. How many poles? Be careful.
2 poles.
How many people say 2 poles? How many people say 3 poles? Okay. Fine. So, to determine how many poles we have, right, what do we need to do? We need to determine how many independent degrees of freedom we have. Or one way to see that is to see how many different initial conditions I can define. So if I set the voltage of this guy to 1 volt and put this one at 2 volts, so just basically I'm using 1 and 2 as arbitrary numbers essentially. Right? Can I make this one, well, can I make this one 3 volts this way? No. The voltage is determined already, right? This voltage is 3 volts from here to there, so I can't make it 4 volts or some other number. Right? So once I determine this initial condition and that initial condition, this one is fixed. And another way to see that is that you have a capacitive loop. Because if you have a loop consisting purely of capacitors, then if you determine the voltage on n-1 of them, the nth capacitor voltage is already determined, KVL. So you have 2 volts. How many zeros? Well, if I short circuit this one, do I see would I get a non-zero transfer function? No. If I short circuit this one, would I get a non-zero transfer function? No. So there's only one capacitor. But I'll get a non-zero transfer function. We saw this when we were doing the first order model for this without these guys, right? We've done that before.
Well, if you short C low, you get zero out.
You get zero output, right?
So
You don't get a non-zero transfer function, you get a zero transfer.
Ah.
The only one that gives you a non-zero transfer function is this guy. Now, we can tell even more. Is it left half plane or right half plane? Zero. When we short it, does it change the polarity of the output? Yes, right? Because it was inverted, but when you short it, it becomes non-inverted. So it's a right half plane, zero. So I have two poles, two left half plane poles, and one right half plane, zero. I already know that. Nothing written. So I have to make a gain about at least 50. So if I pick a resistance of, let's say I want to give myself some margin, so if I pick R2 as 2 kilo ohm, that gives me a gain of 80. So I pick that as like a round number. To make this 2 kilo ohms. And this is 1 kilo ohm by design. This is the source resistance, right? So I have everything I need to determine. So let's find out. We started with the basic stage, and we want to see what the bandwidth of this stage is. So how do we estimate the bandwidth of this? We can use the zero value time constant to estimate the bandwidth. So I need to calculate how many time constants do I have? 2. 3. How many poles do I have? 2. So you see their numbers are not even the same. So shouldn't be surprising if they are not the same. Which one do you say is the right one for the pole? Sometimes the poles can be complex. So we need a better place for the time constants. So I need to go back and forth probably. So let's call this tau. Tau pi 0. So to determine tau pi 0, what do I need to do? I need to see the resistance seen by this guy. So you see all of them are low frequency calculations, right? What is the resistance seen by C pi when all the other capacitors and all the sources are not? So this is short to ground, fine. These are not there. So what is the resistance you see from this node to ground? Looking here, you see R pi. Looking this way, right? Looking this way, what do you see? R1. So it's R1 parallel R pi. So this is basically C pi times R1 parallel R pi, which is basically 100 femtofarads times, what is R1? R1 is 1 kilo ohms parallel, R pi is 2.5 kilo ohms, right? So what is that? It's like 700 something. It's 70, so again, 700 ohms, and so basically times that would become 70 picoseconds. Okay, so that's the time constant for this one, 7 picoseconds. Now, how about tau mu 0? Well, how do we calculate it? What is the resistance seen by this guy when all the other capacitors are 0? So what do you see? Do you remember? We had this sets of equations. We had R left plus R right plus effective GM times R left, R right. In this case, effective GM is the regular GM because you don't have any emitter generation, so that makes it simple. So what is R left? What is the resistance from this node to ground? It's basically what we calculate, R1 parallel R pi. What is R right? It's R2 to ground. And GM is GM. So basically it's C mu R1 parallel R pi plus R2, which is R right, plus GM R2 R1 parallel R pi. So it is 20 femtofarads times, this one was 700 ohms plus that one is 2 kilo ohms plus GMR2 is 80, that's the gain, right? GMR, that's the intrinsic gain of the amplifier. By the way, actually the overall gain of the amplifier is a little bit less than that because you have a voltage divider at the input. So what is the DC gain of this amplifier? Just let me calculate it. You can write as H naught is the voltage divider here, which is R pi divided by R pi plus R1 times GM RL. So this is basically 2.5 kilo divided by 3.5 kilo times 80. Some 56-ish or something like that. Do we know what this is? Oh. Something like 50. That's 57. Okay, so that's minus 57. So that's good. And then you have 2.5, 2 kilo ohms here, 700 ohms here, and this is like 80 times 700, which is basically what? 700 times 80 is like 7k times 8, 56 kilo ohms, right? So you can clearly see it's dominated by this term. This is the Miller multiplied term, right? But anyway, so it's like 58 kilo ohms times 220 femtofarads. And if you add that up, basically you are looking at approximately 1200 picoseconds, 1.2 nanoseconds. That's a large time constant. You'll see it right there compared to the C pi. You see, but just keep in mind, this is interesting. This capacitor is 1/5 of that capacitor. C mu is 1/5 of that capacitor. So it's not the size of the capacitor that matters by itself. It's where it's connected that matters in terms of the time constant. Right? So here, you basically have a very small capacitor that causes you a lot of trouble. Now, the other one, what's the last time constant? What's the last time constant? Tau L. Okay? What is tau L? It's the time constant associated with this capacitor. This is almost trivial. What is the resistance seen by this guy? When all the sources are null and all the capacitors are null. What do you see? What is the resistance you see from this node to ground? Well, if you ignore RO, it's R2. If you didn't, it would be R2 in parallel with RO. Well, let's ignore RO. So it basically becomes CL times RL, which is 200 femtofarads times 2 kilo ohms. That's 200 picoseconds. I'm sorry, 400 picoseconds. This is approximately just, well, this is not bad either. I mean, this is pretty large, but this is the culprit. If you want to fix one thing, you have to fix this. Now, let's estimate the bandwidth. Let's see where the bandwidth is. So the bandwidth is approximated by, so omega L is approximated as 1 over sigma tau I, 0, the sum of the time constants. So you have 1600 and change. That corresponds to some bandwidth, basically. You're looking at, if you calculate all of these and add them up, you're looking at 2 pi times 95 megahertz. So your estimated 3 dB bandwidth based on this method is 95 megahertz. Right? Now let's see what SPICE does. Let's actually put this in SPICE. Let's see. So if you can see this. So this is an actual SPICE simulation of this thing. So that if you do a SPICE, simulated SPICE, what you see is that the bandwidth, 3 dB bandwidth is actually 97 megahertz. So we came very, very close actually in this case. Very good approximation. Right? In this example. And you see it's conservative. Because it gave us 95 and that was 97. Now, what else do you see from SPICE simulations? Let's look at the amplitude and phase plot. The amplitude plot, looking at it, you will see 2 regions. You will see, okay. So you see first you have a flat region. This is where it starts dropping. So you have a rate, if you look at it carefully, you see they have minus 20 dB per decade. So that's a classical basic single pole. So you have a pole around here. And then you see there's a second increase in the rate, which means that you have another pole around here, around 7 gigahertz or something. And you can also, the phase response also indicates that. So you go from 0 to minus 90 here, and another drop in the phase. Okay? So it looks like 2 single poles, one here around 90 something gigahertz, 90 something megahertz, and then another around 7 gigahertz. And then you see that the amplitude starts going back from minus 40 dB per decade drop back to 20 dB per decade drop, which means that you have a 0, right? You have 1 0, bring it back to 20 dB per decade, cancels like the overall drop rate of one of the poles. And you can see it's a right half plane 0, because if it were a left half plane 0, it should come back up. The phase should come back up. It's a right half plane 0 because it's dropping again. So you have 3 drops, basically 2 because of the pole and 1 because of the 0 in the phase, and 2 drops in amplitude and 1 increase because you have, so it's very consistent with what you expect. Completely consistent. you know what you're doing, you should get signal. Okay, so, well, this is 97 gigahertz, but let's calculate the cutoff frequency of the transistor itself. What is the cutoff frequency of the transistor? The way we define it. So the cutoff frequency, omega t, is Gm over C pi plus C mu. So it's 40 millisiemens divided by C pi equals 100 in this case. So in this case, it's about 120 femtofarads. So you're looking at, okay, this is a million, this is the femto, so this is 10 to 15. That's 10 to the minus 3, so that's 10 to 12. So that gives you 3 10 to the 11 radians per second. So you divide it by 2 pi, you get approximately 5 10 to the 10 hertz, which is approximately 50 gigahertz. So you took a transistor whose cutoff frequency was 50 gigahertz, and you had an amplifier whose 3 dB frequency is 100 megahertz. You have to remember, this is a 3 dB frequency, right? So its cutoff frequency is, you can calculate its gain bandwidth product, because the gain here is 1. It's the unity current gain. So if you multiply this 100 megahertz by, let's say, your gain of 80, so you're at 8 gigahertz gain bandwidth product, while this is at 50 gigahertz. So you still are not utilizing your transistor to the fullest. You're not there yet. Okay, so what can we do? Well, the good thing, all of this development and all those things, really, one of the major purposes of that is to find what the problem is. But you can see where the problem is. So why is it that this is so bad? We know this, the answer, because we've talked about this before, but just to refresh your memory, the problem is that they have a gain of 80, minus 80 from here to there. So this goes up by a little bit, this goes down by a lot, 80 times larger. So the capacitance sees a voltage that's 81 times greater than the inputs. So it becomes 81 times larger, the first order. It's Miller multiplied. So how do we solve this problem? Well, we can't eliminate this capacitor, right? The capacitor is part of the transistor. It's part of the junction. If you have the junction, you have the capacitor. You can say, okay, I can bias it slightly differently, I will get a different capacitance, but yeah, those are incremental improvements. What can we do that's substantial, topological? Here. Well, maybe you shouldn't get the gain across here. Right? The problem is that you have a lot of gain across this capacitor. Maybe you should get the gain across somewhere where you didn't have a lot of capacitance. You remember that common base, that common gate or common base that we just talked about a few minutes ago, that one didn't have any dominant capacitor, the dominant time constant. Why was that? Because there was no capacitance between its input and output, no explicit capacitance between the input and output. So maybe we can get our gain out of the common base, but the problem with the common base is that its input impedance is very low. It's Rm. If I put that Rm here, if I replace this with the common base by itself, what happens is that the common base input impedance is going to be 25 ohms. And this is going to be 1 kilo ohm, so that's going to kill all of my gain right there. Because the voltage divider will be 25 ohms divided by 1 kilo ohm, so that's like 1 over 40 almost. So it attenuates my signal by a factor of 40 right there at the input. So that doesn't work. So we know we have a trick for that, right? We have a cascode. So we use the common emitter input, but then we add a common base. So maybe I can use a common emitter and a common base combined, maybe a cascode. So this is the V bias. Basically, this is the ground, AC ground. So now, by doing this, I'm actually adding more capacitor, right? I'm not eliminating any capacitors. I'm just adding more capacitors. So remember, sometimes adding capacitors is good. So what do I have? I have the C pi here, which was already there. I've already calculated. It's the same C pi. I have a C mu here, which is there already. I have and then I have, okay, now remember, my collector to ground has a capacitance, I have CJS. So there's a capacitance hanging off up here. CJS, and then there's also a C pi 2, call it, right? And then there's a C mu 2, and then there's another CJS here, which would be again lumped with C out to give you a similar CL. So you get the same CL because I have a 50 femtofarad from the transistor and 150 from the load, 200 out. So there seems to be a lot of capacitors, but how many poles, how many zeros? Well, we can be a little clever about it, or not clever about it. We can do it two different ways. So if you just look at it like this, how many capacitors do you see? 6. So how many poles do you think?
3.
Hmm?
Maybe 3.
Okay, well let's find out. So one way, the brute force way of doing it is basically just looking at the capacitors and putting initial conditions and see if it works out, right? So let's say 1 volt here, 2 volts here. This is not well defined, right? I mean, this is already defined. I know what the voltage across this capacitor is, right? This is 3 volts, it's defined. So I have 2 already. And then I've also defined the voltage across this guy, right? Because this is from here to ground. Actually, if you look carefully, you see these 2 are actually parallel. So I don't even need to think about 2, I need to think about 1. So I can just combine these 2 and call it CE. I have a C pi, that's what is on the emitter. And I have a CJS, so we have total CE, which is the C pi, which was 100 femtofarad, and the CJS, which is 50 femtofarad, so this is about 150 femtofarad. This is 20, this is 100. So far, how many, between these 3 capacitors, which I also absorb this one into, how many poles? How many independent? 2. Then, how about these 2 guys? If I define this voltage, can I define this voltage? Separately? No, right? Because if I put 1 volt here, then this is already 1 volt. In fact, if you look at them carefully, see those 2 are in parallel too. So I actually have a new CL. I have to absorb this C mu into the new CL, the CL prime, which is basically 220 femtofarad. So now, how many poles? 3. I have a capacitive group here, which basically eliminates one of these, so I have 2 here and 1 there. So 3 poles. How many zeros? How many of the elements can I simultaneously, in this case, how many capacitors can I simultaneously short circuit and get a non-zero transfer function? Still 1, right? Still it's this guy. Because if I short circuit this with anything else at the same time, this will kill the signal. This is the only one, so there's only one. And again, since it changes the polarity of the gain, because the gain from here is an inversion, right? It's a right half plane 0. But how does this solve the problem, by the way? If you think about it. Do I still have minimal multiplication here? Well, let's find out the time constant and see what happens. So what are the new time constants? C pi, has it changed? It's tau pi 0. It hasn't changed, right? So tau pi 0 remains the same, so good for me, I don't have to recalculate it. How about tau mu? It better have changed. I mean, I did all of this thing to make it better, right? So how has it changed? What is the R left? R left hasn't changed, right? R left is still R1 parallel R pi. What is R right? What do you see to the right? You used to see R2. What do you see? Rm, right? The resistance up here. Rm. So this has become Rm. It's really alpha Rm, but that's what's an alpha between them? And then what is GMRM? 1. So now I go 700 ohms is the same. 2 kilo ohm becomes 25 ohms. And I get another 700 ohms. So I get a factor of 2 increase instead of a factor of 1 plus GMR2. And we'll see what that means. So let's see what the new time constant is. This is basically, for all intents and purposes, 1.4 kilo ohms. 1.4 kilo ohms times 20 femtofarads is 28 picoseconds, right? So look at this. This even became smaller than tau pi. I went from GMRM is GMRM minus GMRM. GMRM is 1. So it's minus 1. So this side goes up by 1 volt, this side comes down by 1 volt, not 80 volts. And that's why I got a factor of 2. I got 2 of these. 2 times 700 as opposed to 1 plus GMRM times 700. So that improved. Good. But I've introduced now additional time constants. So you have to deal with. So let's see. So I have a tau E. I have a new time constant. Tau E now. Tau E0. Which is basically CE times the resistance. So this capacitance, which is relatively large, 150 femtofarad, times the resistance C from this node in parallel. What is the resistance you see looking to this node? To ground. Because this side is also ground. RM. RM parallel to whatever you have here, which is large. RM. Alpha RM, that doesn't matter. So, so it's 150 femtofarads times 25 ohms. 4 picoseconds. This is negligible. Although it's a relatively large capacitor, it's negligible. Why is it negligible? Because the resistance on that one, that's the lowest resistance node that you have in this circuit. That node now became the lowest resistance node. It's RM to ground. It's like 25 ohms. In our mechanical analogy perspective, this is a node that's extremely stiff. It's not a loose node, it's a very stiff node. Okay? Now, how about tau L? Tau L has actually changed a little bit, right? Because now my capacitance is a little larger because I absorbed that CMU 2. Now here, I don't have, that CMU is not causing a problem because it's not connected to ground. It's not connected across a larger gain. You get from here to there, 0. So it's basically between that node and ground. So it's 220 femtofarads. So it's the same thing as this before. If I keep it 2 kilo ohms, the only thing is that this becomes 220 ohms. So this becomes 440 instead of 400 picoseconds. Okay, let's estimate the bandwidth again. So second attempt. So this is going to be 2 pi, and if you put all these time constants together, you will get about 2 pi times 294 megahertz. So we went up by a factor of 3. Our bandwidth went up by a factor of 3. Which is good. Which is reasonable. But still. So first of all, let's look at the spice and see what spice gives us. So if we can look at the spice, and so this is the spice simulation for now. So what's the bandwidth that spice gives us? The bandwidth that spice gives us is 337 megahertz. So our estimate was still conservative. It was about 294, almost 3. It's a little less than what you actually get, which is good. So you don't overestimate it, you underestimate it. And that's fine. Now let's see if our picture of poles and zeros makes sense as well. So we have a pole around, it tells us if we have a pole around 400 megahertz, if you look at it, then you see a second drop around 40 gigahertz, around 1.5 gigahertz. You see here you have slope of 20 dB per decade, then you have 40 dB per decade, then you get to 60 dB per decade, and then you go back to 40 dB per decade. And then also your phase drops also show you get 4 times 90 degrees, which basically means that you have 3 poles and right half plane 0, which gives you another negative 90 degree phase. So that's consistent with everything that we saw. And you can see that the 0 is very high frequency, basically, happening around here. It's close to whatever, several hundred gigahertz, which just basically makes sense. It's above the cutoff frequency, it's above the FT. You can calculate the 0 too. We have done this before. It's GM over C, the GM over C mu, the frequency, right? Anyway, so we improved it by a factor of 3-ish. Fine. What is now? Can we improve it anymore? Well, we saw that this guy, which was the major culprit, major troublemaker, went from 1200 to 30 picoseconds. So if I wanted to fix one more thing, what would I fix? Which time constant can we fix? Right, this TL, right? How would I fix this? This is basically the time constant associated with the load capacitance. So it means that my load that I have to drive, remember, 150 picoseconds picofarads of it is just basically the load I have to drive. It's part of the problem specification. Does that mean that I am hopeless? No. I have to just drive it with something that's lower, has a lower resistance. You have to drive it with something that gives you a lower source resistance. What is the thing that gives you lower source resistance? What's a good stage to drive this if you want to get a low output resistance from that stage?
A common source.
A common collector, a follower, emitter follower, a buffer. Right. So you need to put a buffer here. So let's put a buffer there. Let's see what happens. So let me put my capacitors back because that was lumping. That consists of lumping of several capacitors. So I have a CMU2 here. Then I put a common collector here. And let's say a bias at an ideal current source, or a very high impedance current source, so I don't have to worry about that. And then I have my capacitor, load capacitor. So C out is sitting here, which is 150 femtofarad. Then I have a C pi 2. They call it a different name. So I want to keep my indices consistent with your handouts. No, okay, they call it C pi 3 actually. That's right. And then there's C mu 3. And then there's the CJS of this one doesn't matter because it's between an AC ground and AC ground. So that I already know it doesn't matter. It's always shorted. So just don't basically show it. Don't worry about that. And then I had this guy hanging off of the output. So it's starting to look pretty busy, right? But I can use my intelligence kind of supposedly to look at it and see what it really is. So first of all, we've simplified this side before, so this side hasn't changed. Let's see if any of these capacitors are in parallel. I think quite a few of them are actually in parallel. This capacitor is between this node and ground. This capacitor is between this node and ground. This capacitor is between this node and ground. So all three of them are in parallel. What did we call that? CC, okay, for the collector. So this is 20 femtofarads, this is 50 femtofarads, this is another 20 femtofarads. So this is a total of 90 femtofarads. Let's call this CC collector. And then I have C pi 3, which is 100 femtofarad. Let's assume I'm operating at 1 milliamp again. And this one is 150 femtofarads. So let's see if this has helped. So now by doing this, I've changed some of my time constants and introduced some new ones. But again, I'm going to ask you the question, the more important question. How many poles, how many zeros? I want you guys to answer this completely. And this is a qualified question. So who's next in the chain of qualified questions? Did we go through this row?
I think I was the last one.
You were the last one. So you guys have also all answered qualified questions? So okay, let's go to the back.
I guess we have 4 poles and 2 zeros.
Okay, why don't you tell us your thought process?
Well, those 3 capacitors around the input transistor, you have 3 capacitors and a loop, which means that you have 2 poles over there.
So you have 2 independent degrees of freedom here. So
and
far.
also we have
between this one and these 3, right? Because once you define these 2 voltages, this one is defined. So 2 independent degrees of freedom so far.
Yeah,
and
and also the same situation for those 3 capacitors.
These 3 capacitors, right? Because if I determine this voltage and that voltage, then this one is determined because these are forming a loop through the ground. So if I make this 1 volt, make this 2 volts, this is 3 volts already. So then I get 2 more. So how many poles? 4 poles. How many zeros?
And the only capacitors that can make non-zero transfer constants are those are the C mu of this guy and C pi of that guy.
Of this guy. So I can simultaneously short circuit both of them and get a non-zero transfer function, right? I short circuit this, the signal goes through here, there, and to the output. And if I short circuit anything else, then it will make the signal 0. zeros. You can say a little bit more actually about these zeros. Are they left half plane or right half plane? So let's look at them individually.
That one is right half plane because you have
We already
the
talked about that, correct?
but that C pi doesn't change the polarity of the gain, so it's left half.
Left half plane. So we have one left half and one right half plane, 0. That's it. Perfect. So we doubled up. You guys have doubled up. Good job. Okay, so let's do the time constants though. Now let's see what our bandwidth estimate looks like. Okay, so tau C pi hasn't changed. The tau pi hasn't changed. Tau mu actually hasn't changed. Tau L, tau E, I'm sorry, tau E hasn't changed. Right? So we've introduced a couple of new time constants. Tau C, 0, which is CC, and the total resistance from this node to ground. What is it? Looking this way, you see R2. Well, ignoring R01. What do you see looking this way, by the way? What do you see? It's an open. You can see infinity, right? Because I put, from a DC perspective, I put a current source here, which means that there's an infinite resistance here. So infinite resistance times beta plus 1 reflected still is infinity. So it's basically R2. So that's simple. It's, and what's the value of this side? 90 femtofarads times 2 kilo ohms. That's 180 picoseconds. So it's relatively large actually. Now in the grander scheme of things. And then there's another one. We have to calculate tau pi 3. 0. This is actually bad notation. We probably should have picked a single letter index, but this is just one index, the whole thing, pi 3. So you can keep it that way. So it's C pi 3 times the resistance seen by this guy. What do you see? Well, there are different ways to do this. If you are in doubt, we have our equations, right? What is the resistance seen from here? It's this resistance plus that resistance divided by 1 plus gm that resistance, right? But if you do that, basically you see whatever R2 plus infinity divided by, and of course I know this is not mathematically accurate, but plus 1 plus gm, the same infinity, so it's basically 1 over gm is Rm. But there's an easier way to see this, right? The easier way to see this is the T model. That capacitor is hanging off of there. There's nothing connected on this end. So it is Rm. So it gives me it's going to give me another very small time constant. So it's going to be it's really alpha Rm, but it doesn't matter. So it was 100 femtofarads times 25 ohms. That's 2.5 picoseconds. Correct? And now how about my tau L? It better have changed, right? I mean, we did all of this for tau L. We introduced all these new time codes. So what is a new tau L? Well, it's C out, in this case, it's it was 440 picoseconds, remember, times the resistance C. What is the resistance you see looking up here?
R2 or beta.
Reflection, remember the reflection, right? It's this guy reflected down here, divided by beta plus 1 beta. So it's 2 kilo ohms divided by 100, it's basically gives me 20 ohms, plus Rm, which is 25 ohms, so it's 45 ohms. So it's basically R2 divided by 1 plus beta plus Rm, which is 150 femtofarads times 20 ohms plus 25 ohms, 45 ohms, right? 45 ohms times that, it's 70%. Okay, that improved, right? Because I isolated my resistance from the output. Remember? It was because of the RL, but now RL is reduced by factor beta. So I made it 2 kilo ohm into 20 ohms. And then I also added another 25 because of the transistor itself. So that's 45. So that improves substantially. So So now, where's the culprit? The culprit is here. It's smaller. It's a smaller culprit, but still, this is going to be the limiting factor. And what is that? What is causing that, really? You see, you're getting closer and closer to some intrinsic capacitance of the transistor and the resistor that you use there. And you use that resistance because you're trying to get gain. We'll talk a little bit about how we can improve it in a second. But it's becoming more limiting because we have to use that resistance to get gain. One way or another, right? So we'll see that in a second. We'll talk about how we can improve that if we were to do that. But let's calculate the new bandwidth. So what is it going to be? If you calculate this, if you add this time constant, you will see that you will have 546 megahertz. And your gain bandwidth product, if you think about it, you're looking at 500 megahertz, half a gigahertz, let's say, times 80, so it's 40 gigahertz. And your cutoff frequency FDU is 50 gigahertz, unity gain frequency for the transistor. So you're getting closer to those numbers, which makes sense. Now, how about SPICE? Let's look at the SPICE simulation. Now there are several poles here, so it's not as easy to see them individually, but you can look at the slopes and determine this. So you can see that in this case you have two poles around 1 gigahertz. And you can tell that from the slope of the phase here. And then you have one around 15 gigahertz, which is here. And then you have a zero. You actually have a pole. You have a pole and a zero around 50 gigahertz. Doing this little thing. So you get the zero first and then you get the pole. Right? The left half plane zero tries to increase the phase, and then that pole comes in and just cancels it. So you just a little bump here. And you don't see it really here unless you zoom in and kind of carefully. And then you have a high frequency. And you can basically say that you will see that you have the effect of the right half plane zero as well. And the bandwidth that you see for this case is 700 megahertz actually. So if you take the 700 megahertz, the gain bandwidth product is now closer to the FT than you thought. And you see, the more you push it, the more conservative it becomes. Right? Because you can't make it give you a more accurate result. I mean, you can't make it be on the liberal side. By definition, it cannot be. So the more time constant that you introduce, then it becomes more and more consistent. So the difference between this and the actual value becomes larger and larger. And I'll show you cases where it becomes tremendously large. A couple of seconds, or maybe. Let's see. But that's essentially, that shows you how you can improve the bandwidth, right? So we have improved the bandwidth. We went from 100 megahertz to like 700 megahertz in practice. We improved the bandwidth by a factor of 7. But now if I were to ask you, okay, well, let's say this is not enough. What would you do? How would you improve it even further? Based on what you've learned. We look at our time constants again. We don't go and randomly tweak the parameters, right? So, what was it? You said something. Did you have a suggestion? Oh, I'm sorry. I thought I heard something. Maybe a suggestion. So, this guy is bad, right? This is clearly causing a problem. This is starting to become a problem. This was not a problem. But it's starting to become a problem. Right? The analogy somebody I heard once used is that it's like drawing up a pond. Right? So, you have like a pond with a bunch of like rocks and all those things in it, right? And then you're trying to clean it up. Just like, you take the big rock out. Right? So you see one boulder in the middle. Just take it out. Right? What happens? Well, the boulder is gone, but the water level goes down. So now you see like 2 or 3 little rocks. Then you take those out. The water goes farther down. You see smaller rocks. And then you take those out. Just like you start seeing a bunch of little tiny things. At some point you just give up. Say, oh, there are too many pebbles. I'm not going to take every pebble out. Right? And you know you've reached the limit when you get to that point. There's no, but still you're not there. I mean, this is pretty much large, and you can do stuff about that too. But this is probably easier to fix. If I were to fix this first, though that's not the right thing to do, how would I do that? What is the problem there?
Do an emitter degeneration.
But that kills my game.
Lower sources.
Use an active load as a resistor in degeneration.
use an active load as the resistance. Well,
Yeah,
then this problem is
still
here, right?
treats your-
This problem is here. The problem is that I have a time constant that's
Yeah.
formed by this capacitor and that resistance in parallel. So if I want to make this time constant smaller, I can't make C pi smaller, I mean, not in a very useful way. I have to make one of these resistors smaller, not larger. I should put it, if I put a generation here, it always makes it larger.
What if you have a common gate input stage, common?
But then the common gate input stage will have killed the gain completely, almost, right? Because it's the voltage divider between an RM and is it fair to say, if I somehow could see a small resistance, let me give you a little bit of a hint. If I could put something here that would give me very small resistance looking into here instead of R1, reduce R1, would that help?
Put a buffer there.
Put another common collector, a buffer. So if you do that, you can actually get rid of the first term. You can make it into something like this. And we can do the calculation, but we are not. Something like that. And then 1 kilo ohm is here. Right? Because now your C pi, which was here, now sees 1 kilo ohm divided by beta, which is 10 ohms, plus the 25 ohms. So that this guy is going to see 35 ohms in parallel with whatever on pi. So it's going to see 35 ohms in parallel with itself. So now instead of being 70 picoseconds, it's now 3.5 picoseconds. That time constant. Of course, doing this, you introduce two new time constants, right? This guy and that guy. But this one's not that bad. Because remember, this guy sees what? Well, if you didn't have this, it could see just Rm. But it basically sees 1 kilo ohm plus 2.5 kilo ohm divided by 1 plus Gm times 2.5 kilo ohms. Which is like 50. No, actually, I'm sorry. It's actually 100. So it's 1 kilo ohm plus 2.5 kilo ohm, 3.5 kilo ohm divided by 100, which basically is 35 ohms. So this one also sees 35 ohms. It's 100 femtofarad. So it sees about 35 ohms. So it's another 3.5 picoseconds. So the two of them together give you only 7 picoseconds as opposed to 70 picoseconds. And then you have this guy, which is like 20 femtofarads. 20 femtofarads times 1 kilo ohm will give you 20 picoseconds. So you have 27 picoseconds total due to this as opposed to 70 picoseconds. So that reduces that by a factor, more than a factor of 2. But that, well, if this was the dominant one, that's still, but then this would really become the dominant source. So what would you do about that? That's a little bit different.
Can you do like a pole zero cancellation?
You can do a lot of things. You can do a lot of things. True. I mean, pole zero cancellation is easier said than done, right? You have to, I mean, there are ways to do that, but you have to think about it more specifically. The problem is that I'm getting all of my gain in one place. If this were an open loop amplifier, if this were not a closed loop amplifier with feedback, then I don't really have to force myself to do that. What if I got all my gain in 2 stages? Let's say I want to get all of this gain in 2 stages. So if I want to get a gain of overall gain of voltage gain of 80 in 2 stages, what would the gain of each stage should be? What should the gain of each stage be? Less than 9, right? Square root of 80. Let's say 9. So if I want to go from gain of 80 to gain of 9, I can scale this resistance by a factor of what? Almost a factor of 10. So I can go from 200 to 2 kilo ohms, 200 ohms. If I go from 2 kilo ohms to 200 ohms, then this time constant goes down to a factor of 10. So I can have cascade of 2 stages. So I can basically make this 200 ohms, make another one of these stages right next to it, and then buffer it and go to the output. And if I do that, I substantially improve my time constants. I'm introducing more poles, I'm introducing more time constants, but they're all higher frequencies. And if it works twice, what is there to stop you from doing it multiple times? In fact, you can say I can do 3 stages and do the cubic root of 80 in each stage. And you see that you get more improvement, you get some more additional improvement, it's not as much as the first time. And if you actually take this exercise, and it's an interesting exercise, see, what is the optimal gain per stage? There must be an optimal number, right? Because it can't be 1. If you put like infinite number of stages with like 1 plus epsilon back to back, that's not not going to have very good bandwidth because it has infinite poles. It has a lot of poles. So there's an optimal actually. We can calculate. And we'll do some of that in next quarter, but when we talk about that. But I can give you the answer. The first order answer, does anyone know what the answer is? What's the gain per stage if you want to get the maximum bandwidth? Of course, that's not the best power trade-off. Because then you're burning tons of power. Each stage is burning. But do you have a guess of what that number would be? Just take a guess. It has to be a mathematical number, right? It's E. 2.7. It's actually E, if you go with the basics. And if you make that, it would be very high bandwidth, but it would burn a lot of power because you have to get E to the power of n. Right? So, but anyway, so that shows you an